to another one. I hope you all are doing good. And in the previous session, we discussed about what is SD-WAN and how it works in comparison to the traditional WAN. In this session, we will be speaking about the components and architecture of SD-WAN, which was another topic that we had to discuss. But yeah, so let's get started with it.
If you enjoyed the content of the video, don't forget to like and share the video and subscribe to our channel.
So in the components and architecture of SD-WAN, you need to understand how the Cisco's SD-WAN works and what all are the components that comes along with it. So there are four major planes which the Cisco's SD-WAN provides you. Number one, we have the management plane. Second one is the control plane. Third one is the data plane. And fourth one is the orchestration plane. And if we speak about the component that deals with every plane, the management plane is taken care by its component called vManager. The control plane is taken care by something called vSmart. The data plane is taken care by vEdge, or you can also call it as cEdge. And the orchestration plane is taken care by vPond. So these are the total four components that comes along with the SD-WAN solution. How does the architecture looks like for this particular solution? In that case, so there are, let's say you have various sites which we already discussed about like this. So in that case, if you have a site in Bangalore, another site in Delhi, another site in Mumbai, and another site, let's say in Pune. So all of these sites do have some WAN edge devices, and then they're connected to the ISP fabric either by using iNet or by using MPLS or by using 4G or 5G, right? Considering the cellular services. So these WAN edges do connect there. And then there are going to be a set of SD-WAN controllers. If we speak about the specific controllers, then you are going to have vManager, vBond, and vSmart. Along with that, you are also going to have an admin machine that actually interacts with the vManager. The vManager, vBond, and vSmart all can be something which is hosted together, right? It can be deployed on-prem, which means on premises. It can be deployed on cloud, and it can also be deployed in a multi-tenancy environment. However, discussing multi-tenancy is not a part of our course, but yeah, it is supported onto Cisco's SD-WAN fabric. So that's how the common architecture looks like. So all of your WAN edge devices are going to be in control of these controllers, although the planes are distributed across them. So when we speak about the vManager, then the vBond and the vSmart, right? These three planes The management plane or the vManager basically takes care of management plane. Then the vBond takes care of orchestration plane, and the vSmart takes care of control plane. After that, all these managers are just going to be taking care of the data plane, which means actually forwarding traffic from one point to other point. That's how the entire infrastructure is built up. So we will be discussing about each one of the planes and the operations. How does it actually work in the Cisco's environment? The very first thing that we will be speaking about is the data plane. Let's try and understand how does the data plane work. So traditionally, in traditional networks, the communication works or the data plane is composed of devices which have physical interfaces, and our physical layer basically plugs into various type of interfaces, be it the Ethernet interfaces, be it the fiber interfaces, be it the serial interfaces, and so on. And over here in the SD-WAN fabric, your data plane is nothing but the WAN edge devices. And there can be two types of WAN edges. Number one is something that we refer to V edge, and number two, something that we refer to C edge. If we speak about V edges, then we refer to Viptela WAN edge devices, which means the devices which are manufactured by Viptela, and it runs Viptela operating system. C edge, however, is something that is manufactured by Cisco. So we have Cisco's WAN edge devices that can be part of the fabric acting as the data plane. And those are going to run the iOS operating system, iOS XE to be very specific. The devices, the WAN edges, can either be deployed in a physical environment or in a virtual environment, which means not necessarily that these devices are required to be physical. If they are not physical routers, they can be operating systems hosted in a virtualized environment and still can act as WAN edge. But the data plane is where the SD-WAN overlay kind of resides, right? And each router will form the data plane connectivity to the other routers within the SD-WAN overlay for the purpose of transporting the user traffic. So how does that work? Let's try to understand that. So if you have one WAN edge device, let's say this is our WAN edge number one, and that connects to a couple of transports. So that's our iNet, assuming that it's commodity internet, and then we have MPLS. Apart from that, we also have something called WAN edge number two that connects to same both transports. And then we have the LAN segments, right? So this is our branch number one. And this is our branch number two. Geographically, they can be far away from each other. The branch number one WAN edge router have certain interfaces. Branch number two also have certain interfaces. Let's name them, assuming that this is GE0/0. This is GE0/1. Then this is GE0/2, GE0/3, GE0/4. Similarly, we have GE0/0, GE0/1, GE0/2, 0/3, and 0/4. We can divide this WAN edge then into two parts. One is the LAN segment and the other one is the WAN segment. Similarly, this WAN edge can also be divided into two parts, WAN and LAN segment. The end goal is to make communication from the LAN segment of one branch to the LAN segment of another branch secure. But how does that work? So like the solution says, the data plane is where the SD-WAN overlay resides. What does that mean is, whenever your WAN edges are forming up the overlay tunnels, which will be secured by IPsec or a GRE. These two are the overlay encapsulation options that we have, out of which we are definitely going to use IPsec, it being it being more secure way of implementing it. Nobody really implements GRE to secure or to form up the overlay communication between the WAN edge devices, right? So when your WAN edges have created the overlay tunnels with each other by using either of the transport, if you have a dual transport connectivity, more likely your WAN edge one is going to create tunnel from here and here and also from here and here. So there will be two IPsec tunnels between two WAN edges. And once these tunnels are formed, then you can say that we have data plane connectivity. So data plane connectivity is provided using IPsec tunnels. When this overlay connection is established, that overlay tunnel will only be used for forwarding the user traffic from one point to the other point. Okay, which means assume that we have the LAN segments and we have certain addresses there. So this is 11.1.1.0/24 network connected on the backend. This is 12.1.1.0/24 and this is 13.1.1.0/24. On the other side, similarly, let's say we have 21.1.1.0, then we have 22.1.1.0, and we have 23.1.1.0. If we say that this network belongs to sales department that is available in the organization, this network belongs to marketing department, and this network belongs to R&D department. Similarly, this network belongs to sales, marketing, and R&D. So if the sales department wants to communicate with the sales department on the other end, the marketing department wants to communicate marketing of other end, and R&D wants to communicate to the R&D of other end. All this communication will flow inside the tunnel, inside the IPsec tunnel that will be formed between the WAN edge devices. But there is also an important aspect that you need to consider here. Since all the communications are going to be secured, your SD-WAN solution also provides you something called network segmentation. And how does it do that? So in the SD-WAN environment, the term VPN, which is virtual private network, refers to something that we know about VRF in our traditional network, right? So why do we use VRF? For those of you who are pretty much beginner to intermediate level in the routing and switching enterprise or in the traditional network, I'll give you a scenario to you guys. Let's say that we have an ISP. An ISP is providing its services to two customers. We have customer A and we have customer B. The customer A has an office in Bangalore. Customer B also has an office in Bangalore. Similarly, customer A has office in Delhi and customer B also has an office in Delhi. The customer A will have some WAN edge routers. Customer B will also have it. Now let's say that customer A has some internal networks, which is 192.168.1.0/24 and 192.168.2.0/24. Over here, customer B. Now these are private addresses, right? Just a minute. So these are private addresses that we have. The customer A and customer B both can have 1.0/24 being used here and 192.168.2.0/24. Since this is completely customer A's network, this is completely customer B's network. Customer A using the ISP private network wants to distribute the routes. So the communication between this network and this network will only be possible if these routes are exchanged from one point to the other point, right? And specifically, both of these customers are going to be connected to the same router on the ISP side over here also. And internally, the ISP routers will be connected using their own ways of communication, maybe this way. Right? So your traffic, in order to reach from Bangalore to Delhi, it can take this path, it can take this path, or it can take this path. ISP is going to ensure that you have multiple paths in order to reach out from one point to the other point. But when this route, 1.0 route, needs to be advertised out to the WAN edge router that is present onto the other side for customer A in Delhi, and 1.0 of customer B also needs to be advertised out. Both of these routes are going to be given out to the provider edge router, and thus the provider edge router will then forward that route out to the provider edge router onto the other side, which is provider edge 1 to provider edge 2, assuming that it works. In that case, when 1.0 from customer A is also received and 1.0 from customer B also received, this router can get confused, okay, that what is the correct route. I cannot really have same prefix being received from two routers. I need to choose one best router. To avoid such scenarios, the provider edge networks or the provider networks use something called VRF, that is virtual routing and forwarding. By using virtual routing and forwarding, instead of maintaining one global routing table, your router will maintain multiple routing tables for separate customers. So since it's going to be using an interface, if this over here uses G0/0 and G0/1, we can make an interface participate into one VRF or one virtual routing table and another interface participating into another virtual routing table. So in our case, we will assume that our G0/0 interface participates into VRF A, okay, and G0/1 participates into VRF B, which is a routing table that is created for customer B. And then it will learn any routes. For example, the route that is coming from 192.168.1.0/24 is going to be stored into the routing table that belongs to VRFA. And similarly, 192.168.1.0/24 will also be stored in VRFP that comes from. So any route advertisement that happens on this link will directly sit into VRFA routing table. Any route advertisement that happens over this link will directly sit into the other routing table. This way, your single router can maintain network segmentation for different customers. Similarly, in the SD-WAN infrastructure, the VRF related implementation is done by using VPN. Not like that the IPsec VPN or virtual private network. The context of VPN over here in SD-WAN scenario is different. So in that case, every internal network, right? Every internal or external WAN interface or LAN interface must be part of a specific VPN. So there are three types of VPNs, or you can say there are three types of VRFs that we have here. Number one, we have transport VPN or VRF, whatever you say. Second one, we have out of band management VPN. And third one, we have service VPNs. And every VPN needs to be identified with a number. So the transport VPN will always be something called a VPN number 0. The out of band management VPN will always be something called VPN 512. And the service VPN will be anything from VPN number 1 to 65,500, or rather, since we have 512 in between, so 1 to 511, and then VPN number 513 to 65,528. These meaning service VPNs can be created. Transport VPN is just one, VPN 0. Out of band management is also one, VPN 512, but service VPNs can be as many as these. So every interface that is present onto your WAN facing device, onto your WAN edge, must be, I'm saying must, okay? It's not an optional requirement, or it's not an optional configuration that you can fulfill, but it is a must requirement, must have requirement, that every interface must be part of any specific VPN there. Out of which the transport VPN is used for all the WAN facing interfaces. Okay. The service VPNs are always used for all the LAN facing interfaces. And the out of band management will all be management interfaces. Okay, which are completely optional to implement. You are definitely going to have your WAN facing interfaces, you are definitely going to have your LAN facing interfaces, but to have VPN 512 interfaces completed fully functional, that's kind of an optional config. You can avoid that, since your entire WAN edge is going to be managed by vManager, which is one of our controller. You do not really need to have a specific interface like a G0/5 interface that is connected to a PC, and this interface can be part of VPN 512, right? And that's a complete optional requirement that you can fulfill if you want. So with this given overview, what we need to do is our G0/0 interface will be part of VPN number 0. Our G0/1 interface will also be part of VPN number 0. Over here also, this is going to be VPN 0 and VPN number 0. And then all your LAN sided interfaces, they can either be configured, for example, the sales department is configured as VPN 1, which is this interface then. The marketing department is configured as VPN number 2, which is this interface. And the R&D is configured as VPN number 3, which is this interface. Similarly, it can be VPN number 1, VPN number 2, and VPN number 3. And when we segregate the VPNs, it's not like it's not like that one VPN can only have one interface. No, all of these interfaces can also be part of VPN 1 only. But since we are achieving segmentation, where we do not want our sales traffic to talk to marketing traffic and marketing traffic to talk to R&D and each other, we do not want that. We want segmentation in our networks, where the sales can communicate with the sales on the other end, the marketing can communicate with marketing on the other end, and the R&D can communicate to R&D on the other end. We will put these VPN configurations in a way that only whitelisted communications are allowed. With that being implemented, your VPN 1 will speak to VPN 1, VPN 2 will speak to VPN 2, and VPN 3 will speak to VPN 3. So which provides you network segmentation that by default no inter VPN communication is allowed. no inter VPN communication is allowed by default. Only same VPN communication will be allowed. Even if you have multiple interfaces, your G0/2 cannot even speak to G0/3 locally because both of them are part of different VPNs. And for each VPN, there will be a routing table. So 11.1.1.0 prefix will be learned into the VPN1 routing table. 12.1.1.0 will be learned into the VPN2 routing table. That's why there won't be any information about 12, 13, or these outside networks into VPN1 routing table. That's why it won't be able to communicate with them. Well, then how does the communication function in the overlay tunnels and all? We're going to talk about that in the coming sections, but this is quite an important part. Now, another thing that you need to take care of is VPN0 cannot be configured onto the LAN side, and service VPNs cannot be configured onto the WAN side. Why is that? Because you are going to require tunneling capabilities for your WAN facing interfaces, right? There will be IPsec tunnels that will be formed. There will be some other DTLS tunnels that will be formed. All these tunneling capabilities are only provided in the Cisco's SD-WAN fabric for interfaces which are part of VPN0. If your interface is not part of VPN0, it is not going to have any tunneling capabilities with itself, right? So tunnels can only be formed using VPN0 interfaces. That's why we call them as WAN facing interfaces. You are neither going to require any tunnel on the LAN side, of course. So that's one thing that you need to take care of. So the network segmentation is provided, and since your communication between the branches are going to be flowing from service VPN traffic to service VPN traffic on the other side, it will flow inside the tunnel by using either of the interface, by using iNet, by using MPLS. Doesn't matter what transport you're using, since SD-WAN provides you the transport independence. Same level of security can be achieved on commodity internet. Same level of security can be achieved using MPLS or any cellular service that you have. You're going to have connectivity in this way. Now, another thing, what all are the devices that can be part of your fabric, right? From Viptela or from Cisco, which are those devices? So if we speak about them, we have Cisco's WAN edge devices, or I can say C edge devices, and we have Viptela V edge devices. On Cisco side, you can have Cisco ISR 1000 series devices. You can have ISR 4000 series devices. You can have even ISR 8000 series devices. Then you can have ASR 1000 series devices. All of these are physical devices. You can even have CSR 1000V, right? Which is kind of a virtual appliance that you can deploy. So all these runs iOS XE SD-WAN operating system. And on the Viptela side, out of which, however, these devices are physical, which means physical routers, and this device is virtual. So it can be deployed as a bare metal deployment or virtualized deployment, right? It's possible. And on the Viptela side, we have 100 series, we have 1000 series routers, we have 2000 series routers, and 5000 series routers. Along with that, you also have Viptela V edge device. Oh yeah, Cisco also has something called ISR-V, which is virtual, right? That also runs iOS XE. So yeah. And these devices runs Viptela operating system, out of which these devices, these devices are physical, and these devices are virtual. So it's kind of an overall list. These are not all the devices that are compatible. I will also show you the lab listing of all the advantages that can become part of the fabric. That was just an overview of the devices which can become part of the fabric. So that's about data plane. The major takeaway in the data plane is all of your advantages are going to form an overlay tunnel between the branches, and the overlay tunnels will only be used for forwarding the user traffic. Each vantage will form a single or double or triple depending on how many transports you have. It has capability to form single or multiple overlay tunnels with the other branches in order to forward user traffic from one point to the other point in a segmented environment. That's been all about for this particular video. I hope you enjoyed what we just talked about data plane architecture. Moving further in the next video, we will be discussing about the control plane. Then coming forward, we'll be having management plane and orchestration plane functionalities. Let's see how that goes up without making this particular video too lengthy. That's all that we had to talk about. And I hope you enjoyed the content, and I'll see you in the next one. Thank you.